Okay, so a little bit of update. So online, I tried to, so far in every unit, I added to the top of each unit a study guide so that later, as we approach the midterm, the final exam, you'll be able to go to the top of each unit and then see kind of the things that I want to make sure you know coming out of every unit. So if you take a look at that ahead of time to studying, maybe that'll help. It also summarizes, what were the readings for that unit, what were the assignments, and so on. So hopefully that is helpful. For the first unit comprehension assignment, assignment A, that will be due soon. So make sure you take a look at that. That's just an auto-graded assignment, a bunch of multiple choice questions about, the causal loop diagrams, feedback loops, causal links, those sorts of things. And then the big reminder, which maybe I'll make a note of that here. So I'll move this down a little bit. And then so the big reminder here is that on Tuesday, we have no class, so that instead you have time for what I'll call a system scavenger hunt on campus for assignment B, the comprehension assignment for unit B. So basically on Tuesday, don't come to class. I won't be here. And instead use that 75 minutes to go out onto main campus and find a system. It doesn't have to be anything too special. It just has to be a set of variables or components that are interrelated that provide some kind of emergent function due to their interrelationships. Because then in that assignment B, what you'll be asked to do is describe the system you found. And hopefully it would be nice, but it's not required, but it would be nice if you include a picture of some aspect of the system or two of them or whatever to make the description more clear. So here's a component that's in the system. Let's say you could use this or whatever. Let's say you went to Starbucks, you could take a picture of the line, or something like that. And then you could tell me about a system involving how that line is processed or whatever. And so you'll have to come up with, okay, so here's my system. And then you'll have to come up with variables, endogenous, exogenous, and excluded. So basically you're going to build a little causal loop diagram. And in that causal loop diagram, you're going to have to decide what small section of the system do you want to model. And those will be your endogenous and exogenous variables. And then I want you to list a couple of excluded variables, things that you've left out of consideration because you were only focusing on this kind of small subsystem. So you'll describe the system, describe the variables, give me a little causal loop diagram. You can draw it however you'd like. If you want to hand draw it very legibly, that's fine. If you want to use PowerPoint or some other drawing tool, that's fine. Inside the assignment, I've added a link to Insight Maker and VinSim, which are tools that when I teach 212, those are the tools that we use to draw causal loop diagrams. And so my Insight Maker link actually links to a video where I give a quick little tutorial on how to use Insight Maker, a web-based tool to draw causal loop diagrams. But again, you can just draw them however you'd like, just so long as you've got all your links labeled and all of your feedback loops labeled. So you have all the variables in your exogenous and endogenous, all your links, all the labels, all the loops, all the labels, and that's all you'll need for sort of full credit. And then for bonus, I ask you to to have selected a system that matches one of the archetypes that we're describing in this unit. So maybe you found a fixes that fail archetype. Maybe you found an escalation archetype. Maybe you found a tragedy of the common. And so you'll point out to me how your causal loop diagram fits that archetype. And if you have any comments then about traps or leverage points or whatever, it's great to include that. You want to see an example of what I think a great submission would look like. I wrote one up and it's linked from the assignment page. And so you can click on that. It's just a 2-pager where I picked a system having to do with student enrollment and faculty hiring. And I drew a little causal loop diagram. I listed my variables. And I even then linked it to an archetype. So you can use that as kind of a model of what we're kind of expecting. So that's kind of the big thing. So I just wanted to provide you time during the day where you could walk around campus and find these systems. So you can think of it as like a field trip without me. So any questions about that? Yeah. Oh, that's a good question. So is it easier to start with an archetype? And like, if you want to go all the way through and get the bonus to match an archetype, it's easier to start with an archetype and then look for it, or start with the system and then look for the archetype. And I don't, it's hard for me to say as a general rule which one's easier. I would say if you notice a particular problem, like there's, say, some resource on campus that is always depleted, like you always go there and there are never any of, in theory, you have free access to some resource on campus, copy paper or something, but whenever you go there, there's never any copy paper. That indicates to me that there's some systemic issue, and maybe it's a tragedy of the commons, I don't know. So if you have something in mind like that, like an annoyance on campus, you can probably think about, why is this annoying? And that might sort of suggest a particular archetype, and that would be a great way to go. But I bet if you wanted to say, like, there are a couple of simple archetypes, like fixes that fail, that are kind of like, fixes that fail, as we'll talk about, is like you've got a short-term fix, but then in the long term, there's a problem that comes back to haunt you. And if you start with that, you can probably think of a bunch of things on campus that are kind of like that. But it'll take a little bit of thinking. It's not going to be immediately obvious, but maybe it has to do with the walk-only zones and how they're enforced, or the scooters that were on campus that are now off campus, or something like that. But so I think for some people it'll be easier going one way, and for others it'll go the other. But both are totally fine. Any other questions? Okay. All right. So, and of course, the standard weekend reminders. So there's a Muddy's Point, due on Sunday. Oh, that was the other thing I guess I should mention. There's no readings next week because there's only one class, and that class will be lecture B2, the second lecture of Unit B. So this lecture, we're going to introduce archetypes, and then on Thursday, a week from today, I'm going to go through some real world examples and how they fit into that. So that'll provide us some practice in matching those things up. So it's a plus that there's no readings next week, and so next week's the only week I have planned for the semester, aside from midterm week, where there's no reading. But the downside is the week after that, there's 2 readings. And that's the only week this semester I have planned that has 2 readings. And I tried to split them up, but I just couldn't get the schedule to work. They're not very long readings. So what I would encourage you to do, if I've already made the first reading available, and I still have to do the reading exercise, but it's on perusal, is that if you have time next week, just start the reading for the week after that, so you can get that out of the way as if it was next week. So, and I'll get that reading exercise up as soon as possible. So maybe I'll write that down here too, just to have it archived. Make a little room. So the other reminder is no readings next week, but 2 following weeks. So maybe read ahead. Okay. Add a little separation. Hopefully that's readable. Okay. All right, so I want to get to the readings that were for today, but we didn't get all the way through feedback loops before, and I want to make sure that we cover that and we're pretty clear, because the feedback loops are kind of the most important part of these causal loop diagrams. And so last time, we're sort of setting up causal loop diagrams. So just as a reminder, variables are, noun phrases that are, we'll say, measurable and so you wouldn't want to put ice melts as a variable, but you might put sea ice as a variable. You wouldn't want to put increased sales, but you might put sales. So it's those sorts of things that have a quantity. So it's hard to measure increased sales, but it is easy to measure sales, and you can watch sales increase as other things in the systems increase and decrease. So those were our variables, and then we finished up talking about the causal link between variables, like A is a cause of the effect we call B, and we might mark it with a plus or same, or we might say X is a cause of the effect we call Y, and we might, or X, A has an effect on B, X has an effect on Y, and then this idea here is that if you get a change on A, here you get same direction change on B. And then likewise for X and Y, it's the flip of that. So this is the opposite relationship instead of the same relationship. And so the idea here is these are not correlational. So you have to have some reason to believe that it may be that A increases and B increases, and there is a correlation, but when you draw the link, you're saying something stronger. You're saying that the change in A caused the change in B. And that's how you're modeling how the system works. And so those are our causal links. So any questions about those before we get into the feedback loops? And this is all, just as a reminder, this is all causal loop diagrams. And some people just abbreviate, so we'll call them CLDs. Some people just abbreviate them causal diagrams because you don't have to have a loop for it to be a causal loop diagram, but you use the diagram to find the loops. Because as we've learned in the reading, these archetypes are really all about patterns of loops. And so the loops are the important things to find. So it's for finding loops, not for necessarily drawing loops. Some really simple CLDs may not have any loops in them, but they're still CLDs. All right, so then our question here is, what about feedback? So I'll just start a new page here. So feedback loops. So we'll just put that on a new page. And so the idea here is a feedback loop starts, you pick a variable and it starts and returns to same variable with while only visiting other variables once. And so as an example, if I had like A, B, C, D, E, F, and let's say there's a causal link from A to B, from B to D, from D to E, from E to F, from F to D, from F to C, from C to B, and maybe then from C to A. And I would all label these links. So I'll just say arbitrarily here, just assigning some polarities to these abstract things here. So each one of these are noun phrases in my system. Then I need to find the loops. And so I can highlight those. I can say, well, I've got a loop over here. I can pick any variable in this exchange here. D goes to E, E goes to F goes back to D. So there's one loop. And then I look for other loops. And so in the middle here, my eye kind of looks at this and says, well, this looks like it might be a loop, but I can't actually get around it because if I go C to B, B to D, but now I can't go down from D to F. So that is not a loop. Over here, similarly, C, A, B, B, C. Well, I can't go down that link, so that is not a loop. But there is another loop here. Does anyone see the other loop? All the way around, that's right. So I can go all the way around here. So I can go from A to B to D to E to F to C and land back on A. So that would be the second feedback loop. So I can just highlight that, A to B to D to E to F to C and back to A. So you can see that variables can participate in more than one loop. That's totally fine. So it can be tricky finding all the loops. There are tools like VinSim and Insight Maker. These are tools, again, that you'll learn to use in like SOS 212. They actually, once you draw these diagrams, you can ask the computer program to find all the loops for you, and it will make sure it finds all of them, because sometimes it's easy to just miss one of them. So, so I promise that if I ask you to find loops, I'm not going to be too tricky. This is about as tricky as I'm going to get. So there will be like a big loop that you have to kind of zoom out to sort of see. But you know, I'm not going to give you huge CLDs that where there's a bunch of like where there's not a whole lot of loops, but there's like maybe a tiny loop here and a tiny loop here and a tiny loop here, and you keep looking around, and it's like one of those random stereo dot things where you're like you're trying to squint to see the loops. Those are the types of things we really need a computer to help us find the loops. But so mine will be relatively basic. So any questions here about finding the loops before we go into how do we name the loops or during polarity? Okay. So there are two types of loops: negative feedback loops and positive feedback loops. And they're named this way because of how variables inside the loop affect themselves later. So a loop is itself like a type of link back to a variable. So if I were to look at, say, this DEF loop here, then I see that D, whenever it changes, I get the same change in E, which produces an opposite change in F. And I never labeled this, so I'll put a little label here. Let's say both of these are pluses on the inside. So D produces the same change direction in E, but produces an opposite direction in F. And F produces the same change direction in D. So if I sort of follow that around, if D is to be bumped up a little bit, if it changes up, then how will that affect the pressure on D later? Well, the upward motion on D is going to create an upward motion on E, which will create a downward motion on F, which will then create a downward motion back on D. So D tries to rise up, but the causal loop pulls D back down. And that's the reason why this loop here is what we would refer to as a negative feedback loop or a balancing feedback loop. Both of those are the same thing. And I'll give you a rule for finding those in just a second. So we call this a balancing feedback loop. But you know, whenever I write B with a little line around it here, that's equal to doing a negative with a little line around it there. And I could do that same analysis for any of these three, is that they each, whenever any one of them changes, the causal network that they're in is going to produce the opposite change on them a little bit later. And that's what makes it a balancing loop or a negative feedback loop. Now, if I look around the outside of this, if I did that same game here, what I have to do is I just have to count the number of negative links. Because it's kind of like negatives, when you multiply them, they become positive and cancel each other out. the same thing happens with these negative links. So this negative B to D link gets canceled out by this negative E to F link. And all that's left over is this F to C link. So because there is an odd number of negative links around this loop, I know that this big loop is also going to be a balancing loop or a negative loop. So the rule here is that negative feedback processes, or we can call them balancing loops, have an odd number of negative links. And if I were to sort of like do this DEF, like if I were to unwrap the DEF loop, say unwrap DEF, I would get kind of a pseudo causal loop diagram. D goes to E, E goes to F, F goes back to D. And if I put all those links in, D to E is a plus, E to F is a minus, F to D is a plus again, then if I think about this kind of linear relationship, which this is sort of a fake causal loop diagram because D is in there twice. But if I think about this, it's kind of, this is sort of D earlier, D early, and this is like D late. Then if I ask what's the net effect of D early on D late, then I can kind of think of this as like, well, this is like, moves in the same direction. So it's like multiplying by +1. This moves in the opposite direction. So it's like multiplying by -1. And this moves in the same direction again. So the net effect is a multiplication by -1. So it's like this loop is itself an opposite relationship. But if one of those pluses was instead a minus, then the two negatives would cancel each other out, and this would be a same relationship or a positive feedback loop. So any questions about that? A negative feedback loop has an odd number of negative links. If it has an even number, it's a positive. Yeah. What I mean by that is if I think of like D is like, D is a variable, like a component in the system. And so I can think of this as this is the state of the system at time t, and this is the state of that component at time t plus a few seconds. So I'm sort of trying to use time to sort of impart causality of a variable back on itself. So if I'm in a positive feedback loop, if I'm in a good mood now, then the various aspects of the world around me might cause me to be in an even better mood later. And so, so my state now might affect my state later. And on the other hand, like my temperature in my body, it's like whatever, 98.6 degrees Fahrenheit. If it gradually increases, the system in my body is going to maybe cause me to sweat more. And that's going to bring my temperature back down. So an increase in my temperature earlier or now will cause a decrease in my temperature later. And that balances my temperature. It keeps it come back right back down to 98.6. Yeah. The third feedback loop, well, so it is another balancing loop, and I would label it right there. Like I would put it right here. And that it might seem confusing because it seems like this is referring to this thing, but we know that this thing's not a loop. So when we see this, we as being fluent in causal loop diagrams know that I need to look for a loop that's going in this direction, and that loop will be balancing. And so it just sort of gives you that kind of cue that there is a loop somewhere that is centered roughly around here. And if I can see that this isn't a loop, then I look farther out and I see it's probably this one. B, D, E, F, C, B. Oh, good. Yeah. See, I didn't even notice that was there. So yeah, great call. Yeah, and that was, I just sort of picked up on the fly. What I would do, thank you for pointing out that we had one more loop, is so I'm gonna highlight this additional loop, maybe in this light blue. How does that, hopefully that's comes out okay. So B, D, E, F, and back here to C. And so that loop there, can anybody tell what, so if we go down through this, it's a negative, positive, another negative, positive. So to me, that looks like 3 negatives. So that is yet another balancing loop. So that's how I would label that. Yeah. Well, I mean, there is a difference. I mean, this is like, what we're saying is there are multiple balancing feedback loops at work here. So we're saying it's almost like, if I go back to the homeostasis example, in the temperature example, regulation example, you can have multiple mechanisms in your body regulating your temperature. There could be a shiver response. There could be a sweat response. There could be vascular, like your blood vessels could get dilated. And all of these things are trying to regulate your temperature. All of them overlap somewhere. Like, let's say this E, let's say E is your body temperature. So they all have to involve body temperature, but one of them might be a quick response involving some mechanisms. Those mechanisms might actually kick off recruitment of other mechanisms that are slower, and those mechanisms might kick off recruitment of other mechanisms that are even slower. So if I had this architecture, which again, I just randomly drew this up here, it's not in my notes or whatever, so I wasn't trying to mimic anything in particular, but where an architecture like this might come out from is if you do have kind of different time scale feedbacks, kind of quick feedbacks, intermediate feedbacks, and long feedbacks. Any other questions? All right, so when we talk about balancing feedback loops, like so you can use terms like balancing. Sometimes people will say stabilizing. There's counteracting. These are all synonyms. In fact, some textbooks will even use a C as their loop symbol. So that also, all 3 of those things go together. Of course, negative feedback is another one. Am I missing any? Regulating and goal seeking is other terms that you see for this. So if you see any of these terms, that should sort of trigger a synapse to think negative feedback. All right, even the term homeostasis, the stasis suggests that things are staying the same, and that's like a balancing. Because of that, then actually some texts even add like little, instead of these symbols with letters in them, they might actually put like a little seesaw or a little teeter-totter inside there. So if you see something like that, that's supposed to depict like a playground, teeter-totter that is balanced. So sometimes you see those things as well. Okay. So one other thing I'll note about, if you notice there's a balancing feedback loop in your system, one of the kind of useful things is just that almost all balancing feedbacks can be conceptualized. You might have to add another variable or two, but to have a goal. So, a good practice is to draw goals for balancing feedback. And so an example of that I'll mention here would be like temperature control. So we've talked a little bit about temperature control. So I can have a desired temp in my house. I'm going to just put that underneath there to save some space, desired temp. I have my actual temp in the house. Maybe I'll put that in the middle. And if my thermostat is going to be able to measure the actual temperature and compare it to the set point that I set. And so it calculates I'll call it a preference gap. Which is basically just desired minus actual. So if the actual temp goes up, my preference gap will go down. If the desired temperature goes up, my preference gap goes up. And what it does is it uses that preference gap to adjust the furnace heat. So if the gap is increases, then the amount of heat produced by the furnace will increase. And then that will eventually increase the temperature in my home. And so this is a balancing feedback loop. And notice that it has this goal explicitly drawn there. Now, there is another balancing feedback loop that's happening that it's tempting to not draw the goal for. And that is the balancing feedback loop that's trying to bring my house's temperature down to the outside temperature. And so in that case, my actual temperature goes into, well, I'll draw the full loop and then I'll show where I could have taken a shortcut. So my actual temperature, I'm going to go into this thing gap with outside, which is just the temperature difference between it and the outside temperature. And so I'll have an outside temperature, which acts like a second goal, and it affects the gap with outside. So I'm saying that the gap with outside, I'm going to say is actual minus outside. And if that's large, then I get heat loss to the outside. So if the actual temperature goes up, then the gap with outside will go up. If the outside temperature goes up, then I'm going to get less heat loss. And so the gap with outside will go down. And then that gap with outside, that goes into a heat loss. And that heat loss goes back to actual temp. So if the gap gets bigger, the heat loss gets bigger. And if the heat loss gets bigger, the actual temperature inside my house gets smaller. So I've got a plus, and a minus. So that's another balancing loop. Now notice that these things that hang on the sides of the balancing loop, they don't play a role in the polarity. They're not in the loop. So I only follow the links that are in the loop. These links interact with this variable, but they don't affect the polarity of the feedback loop. Now, I could have just gotten rid of this gap with outside here, and instead just connected actual temp directly to heat loss. And I could have said, like, if the actual temperature in my house goes up, the heat loss is going to go up. And so I could have just taken that shortcut. But explicitly drawing this outside temperature in helps remind me as a systems thinker that there are two goals here effectively. There's my goal, desired temperature, and there's nature's goal, which is outside temperature. And these two goals disagree with each other. And because of that, what's probably going to happen is that the actual temperature in my house will be stuck between those two goals. It will never actually make it directly to the desired temperature because there's always going to be some heat loss, but it's also going to be warmer than the outside temperature. And where I put, or where the actual stable temperature falls, is going to depend on how strong this loop is relative to this loop. That's the reason we insulate our houses. We insulate our house to make this feedback loop weaker so that this feedback loop can have more of an effect, so that the actual temperature will be closer to desired temp than outside temp. So drawing the goals often gives us more insights when we draw these feedbacks. And by the way, now that we've read it, this is what was in the text you read last night as an escalation archetype. And that's when two balancing feedback processes have different goals. So as one of them gets closer to their goal, it creates a threat for the other one, and it cranks up its activity, which creates a threat for this one, and they escalate. And so what ends up happening is that this variable gets stabilized, it gets balanced, but these variables here effectively never turn off. It's like the furnace will always keep running and the heat will always be lost. So it becomes an engine where this is stable, but these things, if we think of them accumulating over time, these just keep accumulating over time. This balancing loop never settles down. This balancing loop never settles down. Kind of like Cold War with Soviet Union. The same sort of idea where each one kept putting money into developing their military infrastructure. And so they never actually achieved any advantage over each other. So an interior variable stayed stable, but the activity to keep that stable ramped up in both. And eventually it ran the USSR bankrupt and they had to stop. So it's an example of escalation. All right, so any questions about this example? Labeling the loops, labeling the links. Okay, the only other trap that I want to discuss with balancing feedback loops involves delay. And so a simple balancing feedback loop will look like something that has a goal, a gap, a variable you're trying to regulate. So I'll say an outcome, I guess, and an action. And so basically your goal has a positive influence on the gap. The outcome has a negative influence on the gap. The gap has a positive influence on the action. The action has a positive influence on the outcome. And so you get this balancing feedback loop, just like we had above. So ideally, if we were to draw a behavior over time for this thing, so this is our behavior over time graph, so BOT or BOTG, then our goal, like our desired temperature, we could plot that, it's going to be constant over time. But then our actual outcome that, we're trying, our temperature or whatever, ideally, it would do something like this. So this is our ideal outcome, where it starts well under the goal, it rises quickly and it settles down. And at that point, the action goes to zero and we just sit there. But very often there are delays in this system. So there could be delays because of it took you a while to realize what the outcome was. So there's a measurement delay here. There could be a delay, so I guess I could just write that. There could be a possible delay here. There could be delays like, well, once you've calculated the gap, you decide to take an action, but it takes a while for that action to actually kick in. So there could be a delay there. So for example, your furnace turns on, it starts dumping heat into the house. The temperature doesn't immediately start going up. So it's trying to respond to a gap, but there's a delay between its action and the actual temperature. What these types of delays do is they change the structure of this coming out here. And they can do it in interesting ways. So you can get sometimes you can get something that looks like this, very slow response. But then other times you can get something that looks like this, where you have oscillations occur. And if the delays are really bad and you're in one of these scenarios here where oscillations occur, you can actually lose stability. And these oscillations, instead of dying out over time, can actually grow over time. And there's, I won't go into the details of it, but like if you've ever taken a microphone and held it near a speaker and you get a growing sound at one particular tone, that can actually be drawn in a causal loop diagram as reinforcing one tone, having to do with the wavelength of that sound. And basically, by the time that it comes out of the speaker and into the microphone, you get a constructive interference that causes it to grow over time. So all of the other tones actually get destructive interference, they go away, but that one tone, it grows. And it's matched to the particular delay in how long it takes for the sound to get from the speaker to the microphone. And you have to compensate for that if you're an audio engineer. So there are cases where these oscillations can get really bad. But there's, but in many cases, you just get this ringing behavior that dies down over time. So balancing loops with delays. So that's our trap. Balancing loop plus delay can give you oscillations. And often the way to fix it might be to get rid of the delay, but in some cases, it's actually to make the action more sluggish. So if you've ever been in a shower and you turn the temperature up and the water takes a while to change. Maybe you're in an old motel and whenever you turn it, it just takes a while for these things to actually make any changes. Well, you can't do anything about the delay, but what you can do is update your control model in your head so that when you know that if you get like really cold water, maybe you have to wait a little bit in order to take the next action. So sometimes you have to match your delays. So sometimes making a system less responsive can be the right way to deal with the delay. Because if you take a delay that you can't get rid of and you make your system really sensitive, then it's going to overreact when it just needed to wait. It might have been that you're only going to have freezing cold water for a second, and then after that, it's actually going to be pretty close to your desired temperature, and that's when you react to make that little tune-up. So adding sluggishness in response is sometimes a better response than getting rid of delay, because a lot of times you can't get rid of delay. So any questions about that? Balancing loops with delays generate oscillations, and we have a lot of physical or personal experience with that. If you try to think of any time you've been driving a car or driving a temperature dial or whatever, if the system doesn't respond immediately to you, then the best way to control it is often to be less sensitive to differences, as opposed to try to be more sensitive or pull the delays down, because a lot of times you can't control the delay. All right. So the only other note I want to make about these feedback loops is just the other side of things, positive feedback loops. And they have a bunch of names as well. So when we talk about positive feedback loops, these are associated with growth. They're associated with, sometimes we call them vicious feedbacks, but we also call them virtuous feedbacks, depending on context. And that's kind of confusing because it kind of sounds like one's negative and the other one's positive, and they might have a valence, that's, we desire one, but we don't desire the other, but they're both dynamically just positive feedback loops. Reinforcing is another word we use for that, and snowball effect. And we're going to use loop symbols like a plus. We might use an R. Those are the really common ones. Sometimes you actually get like a diagram of a snowball going down a hill. People will do that sometimes. Sometimes you actually get a diagram of a behavior, like a sort of a growth behavior over time plot. So they'll put that kind of inside the loop here. I would say these are the most common indicators for these. And they're just, as a reminder, they have an even number of negative links. So we could have something like A, B, C, and all of these are positive. So 0 is included in even. This is including 0. And so that's a positive feedback loop, but so is D, E, F, G. That's a positive feedback loop. So here we have 4 negative links, but since it's an even number, the ultimate effect of all of these opposite relationships is that by the time the feedback gets back to the variable, it's in the same direction again. And so that's what makes this a positive feedback loop. The big thing about these things is they start growing slowly, but grow very quickly over time. And so that basically tells us that if we have a loop like this, if it's something we desire, if it is a virtuous feedback loop, like word of mouth spread of a product. If I'm selling a product and it takes a while for word of mouth to get going. But if I just wait enough times, then eventually word of mouth will far outweigh the effect that I could get from advertising. But initially word of mouth is very slow, but once I have enough people out there, then it just spreads. But on the flip side of that, you can have vicious feedbacks where if you don't act early, you probably won't be able to control it. Like pandemics, epidemics. That's an example where once you get enough people with the disease, then it just becomes an engine of growth for the disease. But if you're able to stop it early enough, before that engine gets going, then you can really reduce the kind of the damage of it. So, so there's good and bad things about these cycles. Nothing grows forever. So these were always going to eventually be limited. So these are far rarer than negative feedback in nature. All right, any questions about that? And that's because they eventually stop growing when they run out of fuel. All right, so the behavior over time for that feedback loop. Take any variable in the feedback loop and basically it never settles down. So this is like growth, but it also could go the other way. Could be decline, but it just gets faster and faster. So this is for our positive feedback loop. Yeah. Absolutely. So if we have like population and say birth, then we know that as the population gets larger, the number of births gets higher. As the number of births gets higher, the population gets larger. And so we have a classic growth loop there. But eventually there's going to be positive feedback process or negative feedback processes that, so I'll just draw like a dashed line here, that are going to limit. So as the population gets larger, then maybe the amount of food available is less but we know that if there was more food, you could have more population. So there will end up being a negative feedback loop that will ultimately limit the positive feedback loop. That's right. That's right. That's kind of where carrying capacity comes from. But initially, you only notice this. So early in the system, you're not food limited, so it just looks like growth. So this is like some people refer to as R selection or exponential growth. But eventually you get to a point where you become capacity limited. So this is like K selection. And so together, these things are what we refer to as S-shaped growth or logistic growth. So, but this portion here is that. This is like the exponential. Okay. And that's a great question. And that brings up maybe one last thing that I should mention here, because it's a lingo that we'll every once in a while drift into. But if you do have behavior over time of I'll say, yeah, negative feedback or eventually negative feedback, then when we look at those behavior over time plots, we're going to notice these sort of different regions where we might have this growth, but eventually things settle down here. So it's almost as if there's an asymptote that the system eventually hits. So up until that asymptote, we refer to to this portion of the system as the transients of the system. And so we often talk about transients dying out. So in a pure growth scenario, the transients never die out. It just keeps changing over time. And then this other portion that we have here, then if it settles down to a single point, then we might refer to that single point as an equilibrium. But it's possible that it could also settle down into an oscillation. So oscillations themselves, as long as they're not growing, that is also another steady state behavior. So we can have oscillations as well. So in general, this region we refer to as the steady state of a system. And you can view it as not growing. So it can oscillate just so long as it doesn't grow. And if it's not growing, we'll say this system is stable. So even an oscillating system, we still can say is stable. We might say it's so-called marginally stable. And what that means is if we got some of our parameters kind of wrong, then the real system might not oscillate like this. It might have growing oscillations because, so it's almost like the oscillations are almost unstable. But it's not growing, so we still refer to it as stable. So stable systems have a steady state that occurs after their transients have died out. So when we look at these graphs, that's kind of how you should sort of cut it up in your head, is sometimes we can ignore the transients unless the transients do really interesting things. Like it might be that the transient number of sick people in a population gets so high that it overwhelms hospitals. So very often in epidemiology, we think about what happens at the end of the pandemic, how many people got sick. But sometimes it's important to talk about the transients because you want to say during the pandemic, what was the maximum number of people who were sick at any instant of time? And that tells us about hospital capacity. So sometimes we care about equilibrium, sometimes we care about transients. So that's kind of all I want to say about the fundamentals of positive and negative feedback. So any questions about that? So hopefully by now you feel comfortable looking at a causal loop diagram, finding the loops, labeling them as a positive feedback loop or negative feedback loop. And whenever you think negative feedback loop, you have to ask yourself, are there delays that might cause oscillations? Okay. So in these next two lectures, we're sort of focusing and sort of discussing these archetypes that you read about last night. So were there any reflections? Did anyone find this to be a helpful or maybe more difficult set of readings? Anything you want to share about what you got out of it? We already saw them trickle in a few examples of these different archetypes. And then I will give you a bunch more real world examples next week and hopefully make things more and more concrete. If we look at them, I mean, maybe want to bring in the kind of these key archetypes. I do want you to know these key archetypes from the Kim and Lannon article there. So if I could bring those up, and maybe I'll just copy these over and make some annotations on them. So I'll just bring this guy over. Maybe in a second here. Say archetypes. There it is. Okay, so this Appendix A of this article I really like, in that it has a nice summary of these very common systems archetypes or traps that you see up here. So so I just sort of list a couple of these. I mentioned escalation earlier. And what I like about what they've done in the summary here is it gives you an idea of what the behavior over time would be. So this generic result, this again was like the temperature of the house. This is like the furnace heat. This is like the heat loss to the environment. And so we can see that the furnace heat in the furnace never kind of turns off. The heat loss to the environment never kind of turns off. But meanwhile, the temperature of the house stays kind of stuck in between the two goals, the goal from the left and the goal on the right. So, so they describe in each one of these, they kind of describe the general archetype. And these guidelines, these are where you look for leverage points. So the archetypes, sometimes we also call them traps, and say, if you find yourself in this trap, where can you get leverage? And so they mention here to break an escalation structure, ask the following questions. What is the relative measure that pits one party against each other, and can you change it? So can you make it so these aren't fighting against each other? Are there delays in the system that distort the true nature of the threat? So is it actually that these two individuals are in agreement, but because their actions are so out of sync that when one takes an action, the other one sees a delayed version of it, and that delay makes it seem like they're taking opposite actions. what is the deep-rooted assumptions that lie beneath the actions taken in response to the threat? So are they really threats? So they're giving these sort of suggestions for if you find yourself in one of these traps, look here for some possible leverage points. And they do that with all of these. And so before we kind of go through some of the ones that I want to sort of make sure we hit on here, I hope you notice that there are a lot of close relationships between, especially like this drifting goals and this fixes that fail. There's a lot of things that sound similar and loops structures that kind of look similar. And that is why I wanted you to read this other article about the Archetype Family Tree, which I'm going to grab here and pull over so you can zoom in on it. So this, written by different authors here, but what I like about the Archetype Family Tree is it sort of shows how you can build some archetypes from each other. So like if I were to look here, up at the top here, if I know that that I'm looking at a system that is trying to fix a problem, then I almost definitely am going to start with a balancing loop. And there's my goal for my balancing loop. Like I was saying, you should try to always put a goal for your balancing loop. So they give a little kind of like reminder of what that structure looks like. And then they show that you can augment the balancing loop in different ways that represent different problems that might happen. So I implemented a fix, but is it possible that my fix is going to end up in the long term just having me return to the problem? Well, I take my existing balancing loop and I can add a reinforcing loop around it, which has sort of the problem returning. So my fix ends up strengthening the problem in the long run. Alternatively, I can say, well, actually, what if my fix creates problems for some other party that I haven't thought of? And so that implies that I have to ask myself, is anyone else going to be affected by my fix? And if they are, I need to put them in the system. And so then I build up another balancing loop. Here's my original balancing loop. And here's the balancing loop of the other party who's just trying to do what they were doing before I implemented their fix. So I put those two things up there, and now I've got this escalation loop. Other than they show also this drifting goals. Well, so there's two balancing loops there. One of them is the original balancing loop, but then what it's saying here is this goal, that goal itself can change over time. So it might be that if I am far from the goal for a long amount of time, psychologically, I'm going to lower the goal and I will achieve it faster, but I'm achieving a lower goal than I started out with. So this balancing loop on top is one lowering the goal. And this is the original balancing loop on bottom that's trying to bring the system up to the goal. So you can kind of walk through this tree and you see that instead of seeing a bunch of independent archetypes, like in the Kim and Lannon article, what you really see is that there's a whole lot of relationships. There's even some convergent relationships where a fixing problems and a growth end up coming together in this growth and underinvestment problem here. And there's a couple other more of these that like accidental adversaries where you get these archetypes coming together. I'm only asking you to know the archetypes from the Kim and Lannon because there's a couple other archetypes that we haven't gone over, like accidental adversaries, the attractiveness principle, and I think those are kind of the two big ones that are different here. But I'm hoping that the rest of this tree will make it easier to think about all of these. Like I liked that in if I go back to this, at the bottom of this article, they have this journey through the Archetype Family Tree that is related to spending controls. And this is a great example of, we can say that I have a problem that I'm trying to solve, and that is I have a cash flow problem, and I want to reduce my cash flow problem. So I come up with a fix, borrowing. Well, this is a balancing feedback loop. As I have low cash flow, so if I have debt, or if I have bills I need to pay, then I can borrow on my credit card to pay them, and that will get rid of the cash flow problem in the short term. But of course, I have to think, are there other variables that I'm not thinking about here? And the one variable that I'm thinking about here, or that I'm leaving out, is that as I borrow more, I now have to pay interest payments later. So I've just taken this loop and I've augmented it with a variable that I hadn't thought about. And this was originally an excluded variable, and I create an endogenous variable that represents my interest payments. Well, as I have more interest payments, that's going to create more of a cash flow problem. So now I've gone from a balancing loop to a fixes that fail loop. So then I should ask myself, though, because of this relationship between fixes that fail and shifting the burden, was there another solution I could have come up with that now I've made even harder on myself? And so they've just taken this loop and they've rotated it into this loop here. And so that was my original fixes that fail. And then they said, you know what, another thing I could have done instead of borrowing is just tighten my financial controls. I could have spent less. Could have said, you know what, this month, maybe I don't go to the movies. Maybe I get rid of one of these subscriptions, those sorts of things. And if I would have done that, that would have helped my cash flow problem. But now that I'm borrowing, I still could do those financial controls, but I've gotten so used to just using my credit card that I don't see a need to stop that subscription. So that creates this reinforcing feedback loop, which actually ends up hurting my financial controls and increasing my cash flow problem even more. So not only was it a fix that failed, but it also had a side effect that it reduced the chances of me doing what I should have been doing in the first place. And so when we look at the three of these from Kim and Lannon, they look like three separate archetypes. But in reality, there's a nice connection between them. And so when you look at all the ugly extra loops that are being added, really think of it as like an onion that you're layering up. And so you start with a simple balancing loop to fix a problem. You recognize that problem creates, that fix actually reinforces the problem later. And you recognize that there was a better fix, that your fix is now preventing you from going. And that's how you get the shifting the burden. So any comments about this? I know that in the perusal, there were some people who said when they were talking about fixes that fail and shifting the burden, that they seemed really similar and they had a hard time differentiating. And this is sort of the reason why they are related, but shifting the burden acknowledges the fundamental solution and the symptomatic solution together, whereas fixes that fail is only modeling the fixing of the symptoms and how that ends up causing the problem to come back. So we're just including endogenizing or including more of the system to get a better idea of what's going on as we complexify these models. So any questions of that? Is this image, does this make sense? And we can trace it down through here. So balancing loop here, fixes that fail here, shifting the burden here. We're just following down through this tree. Okay. All right, so I do want to cover at least one other thing here. So I like the Kim and Lannon. We won't go through the 4 different ways, but you should know sort of the 4 different Kim and Lannon ways to use archetypes. And I like that because it shows the flexibility of these archetypes. And I really like this idea of archetypes as lenses. where one problem has multiple archetypes. Possible. There is no one right archetype. There are some archetypes that just don't fit, and those don't help us. But the more archetypes we recognize, the more traps that we recognize, then we can look at every problem and say, how many of these traps that we've recognized might apply? And if they apply, then we've got this whole vocabulary of systems archetypes that suggests potential fixes to the problem. And so that brings me to where I want to close, which is tragedy of the commons, just because it is so fundamental to so many sustainability problems. How many people have already taken a class where you talked about the tragedy of the commons? Okay, good. About everybody. Okay, so the tragedy of the commons is, so if you were to like, when we teach about the tragedy of the commons and say SOS 325, which is economics of sustainability, we define goods or resources on sort of this axis of excludability and rivalry. And so basically, there are resources that if you are using it, you can exclude others from using. And so those have high excludability. But there's also resources that if you're using it, you can't prevent anyone else from also using it. So they have low excludability. So, so I'll say this is high and this is low. And so there's also this rivalry, which is if you're using it, do you reduce the benefit of any other user? And so there's some resources, like if I listen to public radio, you don't notice that I listen to public radio. It sounds the same to you as it does to me, regardless of whether I have it on or not. But there are other resources that as I use it, your benefit declines, like a highway. If I get on the highway, I increase the congestion and reduce the benefit of the highway to you. So a common pool resource is one that has it's non-excludable, but rivalrous. This is a commons, the commons or common pool resources. Whereas if it had no excludability, but was not rivalrous, it'd be a public good. And so this is the one we're focusing on here. If it was highly excludable, but highly rivalrous, then we talk about private goods and club goods, but I'm going to sort of leave those out so that we can just sort of focus here on this commons good. And so lots of things fit this. And so in this copier example, on the perusal, I asked a question, there were a lot of sort of guesses to what the common pool resource was. To me, I want you to see that the rush jobs are the common pool resource, because you can choose to rush your copier or not. You have the choice. If you choose to rush your copy job, it will increase the queue time for other people who make that choice. And that's what makes it a common pool resource. And so if we recognize this commons problem, then we can always go back and we can say, well, you know what, the tragedy of the commons, there is an archetype for that. And we kind of know how things might behave over time, and we have a bunch of leverage points that go along with that. And a lot of those leverage points involve getting like a governing board involved and so on and so forth. But anyways, we'll pick up that a little bit on Thursday, not on Tuesday, no class on Tuesday, with some common examples of where these archetypes come into play, as opposed to just another abstract text here. So I won't keep you any longer. The attendance question here is, how many negative, how do you determine a negative feedback loop? Is it what type of link, like what's the rule for a negative feedback loop? I give you a loop, it's got a bunch of links. How do I know that it's a negative feedback loop? and you can summarize it in a couple of words. And that's all I've got for you. So I hope you have a good weekend. See you in a week. Again, no class on Tuesday. Use Tuesday to find a system that you can diagram out for your Unit B comprehension assignment. If you have other questions, feel free to come up. Otherwise, that's all I got. Okay.